Honeywell UOP, or uh, others like heavily rely on this software for their process modeling and simulation. So that's why we chose this software. And let's start with the presentation. So, so the software is named Aspen Plus, and it was developed in the laboratories of the Massachusetts Institute of Technology, MIT in Boston, over the last 50 years. So it started as a classroom project, and today it's a full-fledged company providing the software to a lot of corporates as well as organizations throughout the world. So since I have to also let in people inside, I won't go into the full screen mode for some slides. So what is flow sheet simulation? Simple question, it's a computer program to qualitatively model the characteristic equation of a chemical process. So most of the processes that you would encounter in any bioenergy system would be chemical in nature. There would be a group of compounds reacting to form another group of compounds. Simple chemical equations. So the things that you need to incorporate or to estimate would majorly be mass and energy balance. What is the mass of the different chemicals, compounds, elements going in, and what is the out? What is the energy associated with that reaction? Is it an endothermic or an exothermic reaction? Do I need to supply heat, or would heat be produced in this particular reaction? And there are certain kinds of reaction in which you just can't determine. Take, for example, pyrolysis. It's totally dependent upon the composition of the biomass that the pyrolysis is going to turn out to be endothermic or exothermic. Sorry for this. Okay. So yeah, there I just received a WhatsApp message like people asking me to let them join. So I'm allowing them, but like I'm also giving a lecture side by side, so there would be some delay in case somewhere is left out, someone is left outside. So please bear with me, be patient. I'll be checking who all are there waiting in the lobby, and I will let them in as soon as possible. Okay. So the other thing that we need to keep, if you remember history, your school days or your college days, many chemical reactions would end up in an equilibrium where no further reaction takes place. So this also makes sense to estimate what is the maximum conversion or what would be the equilibrium concentration for a particular system. If I'm giving in these all reactants, where is the system going to stop? Then another thing, rate correlation. How fast the reaction is going to occur. No doubt, all the reactions might reach equilibrium, but it might take days and even months. So can we wait so long? No. So that's what like where the rate comes in. We need to know the rate kinetics, how fast the reaction is occurring, so that we can derive what is the size of the reactor we need. If the reaction is so too slow, probably we can get only a certain amount of conversion. We have to achieve a very big reactor to achieve the total conversion. Then this kind of software also predicts the stream compositions and properties. By properties, I need temperature, pressure, and the different mole flow rates, volume flow rates, enthalpy, entropy, operating conditions. What is the operating temperature and pressure of the operating equipment? The size of the equipment. What is the volume of the equipment that I would need? And finally, the economics and the emissions. You just saw the example of economics and emissions. Okay, so what does Aspen provide us? It provides us ready-made modules for different chemical process equipments, such as heat exchangers, pumps, compressors, turbines, distillation column, absorbers, strippers, and chemical reactors. And many of them would be very important for designing an energy system. And they're much more important when we are dealing with bioenergy systems, because they would necessarily involve turbines or engines if we are dealing with electricity production. In case we are dealing with biofuel production, we need heat exchangers, we need columns, we need reactors. So it's important that we have ready-made equipment available for them or designs available for them so that we save time. We can do the similar things in softwares like MATLAB, but in that case, we have to write the mass and energy balance for each equipment separately, and that would consume a lot of time and also be computationally very expensive. And in this particular software, the user can input temperature, pressure, and the reactor size, and it will compute the conversion, the efficiencies, the performance, the output conditions, the energy use, and finally, the cost. Now, how does Aspen do it? It uses generic equations, and you can change those equations if you need. The best part of this software is that it has a massive database known as Aspen properties, which comes with the software. What this database consists of is the heat capacities, thermal conductivities, viscosities, surface tensions, and various correlations for different compounds. Not all systems would have similar kinds of equation applying to them. They could vary very differently. And you need the constants that would dictate these equations or the different variables that need to go in. And this particular software has all of this. So you don't need to worry about like if I'm using this particular kind of system, how I'm going to get the heat capacities, the thermal conductivities, the conversion values, the rate kinetics. So these can be found inbuilt into this software. And reiterating again, the most important feature of this software is its massive database, which you won't find in other softwares. And the applicability is that like this software allows you to even model biomass, which is absent in the other software of similar type. So let's go to a bit into working methodology. So it's called the sequential modular flow sheeting, which means I design a flow sheet. A flow sheet is nothing but depicting the flow of different chemicals. A similar flow sheet could be I'm giving in a feed and it enters into a flash drum. A flash drum is any reactor which would have an abrupt change in temperature and pressure. And if the temperature and pressure change is good enough, liquid would divide into a vapor phase and a liquid phase. The vapor phase would rise up and escape. The liquid phase can then be pumped. So this would be a flow sheet, a very simple flow sheet. You have a feed going in, it gets separated into vapor and liquid, and the liquid then gets into pumped at a higher pressure. So the normal way this would be solved is it will take in the feed, calculate how much amount of it is going to convert into vapor, how much it gets converted into liquid based upon the different factors, mainly being temperature, pressure, and the equation of states. And finally, it will take in the energy, what would be the electricity consumption for compressing this liquid at the required pressure. But there's a problem. How do we solve a system like this, a flow sheets like this, which have a recycle? You have feed going in, it separates them into vapor and liquid, then a pump. And suppose that I have a split, which again divides this compressed liquid into two parts. One is the part that escapes, and there's another part that's recycled. So how am I going to calculate this? And the way to do is we take a tier stream. Tier means I will break the stream from here, assume some hypothetical values and do the calculations. And this would give me a value here. And we'll see what is the comparison between the two values here and here. Maybe I'll take. Yeah. So we have these 2 points and we'll see what is the comparison. We'll assume a value here as the input and see how does that compare to this. So once we have a value, this is the value that gets replaced here. And based upon the principles of simulation, after a few particular iterations, this would converge. It can take around 100 to 200 simulations, but finally this value would match this value. And this is how the recycle is solved. It's called the tiering of stream. You choose a stream and you can choose a value for that. The solver will keep on guessing new values till the difference between the guess and the solution becomes below that tolerance limit. So for any simulation software, you need to satisfy or you need to give the minimum tolerance level. By default in Aspen, it's 0.0001 or 10 to power minus 4. So that is good enough for simulations like this. And also in most cases, Aspen 1 or Aspen Plus should be able to choose a tier. You don't have to do anything. You just connect the recycles, and you don't need to worry about how you are going to manage with the recycles. But in a normal case, this would be very difficult in other softwares. Also, if you're doing this in MATLAB, or like you have to write a separate code how to go about the steering of this system. Another approach is the equation-oriented mode, which means I'm not going by the sequential modular approach. I have all the system, all the reactors, and I write the reactions or these equations for all of them and solve them simultaneously using matrix algebra. I write the equations for the different variables. All the variables will give me different equations, and normally the number of variables should be equal to the number of equations. And solving that, I'll get an answer. But a system like a power plant that I showed you, like production of ammonia from biomass, could have like maybe couple of thousands of variables and couple of thousands of equations. How are we going to solve that? So that could be very computationally extensive. For a small system, that is okay, but that can't go for a larger system. And also this kind of system would depend upon the initial values. And how are you going to get the initial values? So one approach is that people now are taking is you take a sequential modular approach, get the initial value, and then go to equation-oriented approach, because this is much more faster. But again, like this is computationally expensive. When you go, the numbers of the system size increases. So the good methodology would be you use the sequential modular approach and optimize the parameters using equation-oriented approach. So first use an sequential modular approach, get initial guess, and if case you need to optimize, go for equation-oriented approach, because these are very good for optimization. For today's class, we are going to focus upon the sequential modular approach. We are not going into the equation-oriented approach because that's another another lecture. Maybe next time or sometime in the future we can take up that. So the methodology is that we will solve one reactor at a time, and then go to proceed next, as and when it's going. So Aspen is not magic and does not have the ability to understand your intentions. Like any simulation software, it relies on the principle garbage in, garbage out, which means your answers are always as good as your assumptions. If you are able to provide in good assumptions, it will give you good answers. If you are providing in not so good assumptions, don't expect the answer to be really good. So you need to be giving in sound assumptions to get really good answers out of it. Now there are different kinds of components that it can take in. It's conventional, like conventional, the normal compounds that we come across in a day-to-day life, like hydrogen, nitrogen, methane, and certain hydrocarbons, anything. Solid includes solids like calcium, sulfur, and carbon. It can also take in non-conventional compounds, and this is where we can model biomass. So this is an important feature of the software that enables us to model biomass, which is its ability to model non-conventional components. There are also some pseudo components which are used to model a group of chemicals together. There might not be a real chemical of that composition, but it's clubbing of group of chemicals together. It can also model polymers, oligomers, and segments. And this also gives it the ability to model the cellulose, hemicellulose, and the lignin compounds. I believe you heard about them in the morning class by Professor Sanjeev. Each biomass is made up of cellulose, hemicellulose, and lignin. So if you want to model it, the software gives you that opportunity as well. And then comes to hypothetical liquid in terms of different types of bioils. So, or like different types of oil, which might not be existing, but be a composition of many of oils. So you can model that as well. Now, property packages. Now, you might have heard of the basic equation PV is equal to nRT. Pressure into volume gives number of moles into the universal gas constant into the temperature. That might not apply to all the systems. It's good for an ideal gas, which is rarely found. And like the reference state would be an ideal gas which is 298 or like 25 degrees Celsius and 1 atm. But most of the systems would have a different condition in terms of temperature and pressure, and they might not follow the ideal gas state. For them, we have different thermodynamic models, which will depend upon the fugacity, enthalpy, entropy, Gibbs free energy, and volume. And we won't go again into details of all these things, but they are collectively called a thermodynamic property package. And some of the examples being NRTL, RK or Redlich-Kwong, Uniquac, Pang-Robinson. So different systems would have different types of property packages applicable to them. And this particular software has many of them available by default. And just to give you an example, depending upon whether the system is polar or not, you can estimate. And most of the biomass system would not be polar. And since it's a real system, we would go for these particular types of equations, which are RKS, RK, Peng-Robinson, or RKS, BM, or SRK. But not to mention there are other types of system as well. There are electrolyte systems in case you have electrolytic separation taking place, or a typical example would be the CO2 absorption. Like if you remember the example that we presented for the absorbing of CO2 using MES solvent, so that's an electrolyte system. So that would need a thermodynamic which is applicable here. So in that case, probably I will use the NRTL system, which is here. So all these systems are available. And just to give you an example, like this is what the RK equation looks like. So you might be aware of the PV is equal to nRT. That's not applicable here. When we are going to real system, the equation turns out to be something like this. And the parameters are even more complex. So these equations are readily available, and this helps us come out with the temperature, pressure, as well as the composition of the system at different operating conditions. And yeah, so we also have an inlet health module which can help us choose the type of equation. Like we have the different applications and what are the recommended property packages. And coming to reactors, so it has many types of reactors available, which could be basically divided into stoichiometry, yield, equilibrium, and Gibbs minimization. So by stoichiometry, I mean, I know the reaction stoichiometry. A moles of A compound, B moles of B compound react and give me C moles of C compound and D moles of D compound, a very standard equation. If I know that equation, I will go for stoichiometry reactor. Yield. If I know 1 kg of this compound would give me, say, 10% oil, 10% char, 70% gases, and 10% inerts, I would go to a reactor called a yield reactor. Then equilibrium. If I have really no idea about what the reaction system is going to go. So what I would choose an equilibrium or a Gibbs reactor. I would give all the compounds, and what the reaction is going to do, it is going to give me the equilibrium concentration. If this is the composition of compounds that is going into the reactor at this temperature and this pressure, I should expect this as an equilibrium concentration. It doesn't tell you like how fast it is going to achieve, but this is the reaction composition that you're going to achieve if the reaction system is left for a fairly good amount of time. So if you have absolutely no idea where the what the reactions are or what the output is going to look like, go for the equilibrium, the Gibbs reactor. It will minimize the Gibbs free energy and give you the composition of the different composition which is possible. Plus, if you have the kinetics available, you know how the reaction is occurring or how fast the reaction is occurring. You can go for standard models like CSTRs and PFARs. You can model the reaction and you know what the size of the reactor is going to look like. And the energy balance of the system is also coupled. So you would come to know what is the energy input and the output of this. So again, these are like some of the reactors in concise: stoichiometric, yield, CSTRs, plug. Batch reactor means you put in chemicals and leave them over a time. You have no input and no output. All these reactors would be steady state, means there's a constant input and there's a constant output. And then you have this equilibrium reactors, which will give you the equilibrium concentration. So these are two kinds of reactions. So in the R-Gibbs, you don't give any chemical equation, whereas in R-Equal, you can give a chemical equation as well. So that's the difference between these two equilibrium reactors. Plus, it has a lot of features for handling solids, which would involve like fluidized beds. classifier, granulator, dryer, screening, crushing, crystallizers, and like these crushers, screens, dryers, fluidized bed are something that you would need for any system that would require bioenergy, because these are the standard processes. Then you would have separation columns as well. How do you separate it? And a typical example of separation column would be your fractional distillation of the crude. It distributes the crude into different components, and that is a sort of distillation. And that is an example of a complex distillation. But you can do distillations like this using this software. Have the heat exchangers now. Any biorefinery would have a lot of heat sources and heat sinks, and it becomes very important to link those sources with the sinks to obtain the optimum plant operation. So this particular software has that feature as well. It has all the compressors, heaters, as well as valves, pumps, anything that you would need. Okay, and it also gives you the ability to write your own codes and include that into it. Excel sheets, I'll take an example of this. And then you can do a sensitivity analysis, optimization, and you can achieve your desired specification. Say this is, you want to say like, this is the composition I need to achieve, what would be the required temperature and pressure. So the software would vary the temperature and pressure to get the required concentration. So that ability is also present in it. So with this, let us try to solve an example where we are trying to simulate a gasification process, and the intake would be 1 ton per day, or 1000 kgs, or sorry, 1 ton per hour. And I have the proximate analysis and the ultimate analysis. So I believe you have a basic understanding of the proximate and the ultimate analysis. So ultimate analysis gives us the composition of the different compounds in terms of carbon, hydrogen, nitrogen, chlorine, sulfur, and oxygen. So any biomass can be divided into these six components. And this is basically giving us the elemental composition of the biomass. And the normal composition would be, it will have around 45 to 50% of carbon, as compared to coal, which has above 80% carbon. So that's why the efficiency of biomass as a fuel is very less. It would have around 40% of oxygen, 45% of oxygen. And this is again the reason why the efficiency is less. Almost like half of the biomass is just oxygen, which doesn't have a calorific value. And then again, another 6 to 7% would be hydrogen, which again adds to the calorific value of biomass. So our aim would be, we will try to simulate a gasification process and try to produce electricity from it using the biomass which has this composition. So this composition is basically for wood, for which the gasification process is known to act nicely. So with this, let me share my whole screen. That way you can see. Okay. So yeah, so now you can see my whole screen. So this is to start the software. What I will do is I'll go to the Aspen Plus. It has many more packages, and press Aspen Plus V. So I'm using the 9th version, whereas like a lot of versions are available. The current version that is available in the market is V11. So you can go for either of them. So I would press a new one here, and then press a blank simulation and press create. So I reached this figure. And another important announcement, now I have given everyone the ability to unmute themselves. So in case anyone feels left behind or anyone is unable to get anything, feel free to unmute yourself and ask any doubt that you may have. Okay, so here we are into the software. So we let me give you a brief of the software. It has a left side which has a panel for the different properties. And then we have the main window. And then a bar on the top, very similar to the Word that we had in 2016 or 2017. So the first thing that we need to suggest in this are the different components involved. So the first thing would be biomass. Right here, biomass. And the type would be, it's a non-conventional solid, which means I don't get it easily in the nature. The properties vary with the different composition, and I will tell you like how to go about it. Apart from biomass, after the gasification of biomass, the only thing that would be left behind would be ash. So this again would be non-conventional. So I've defined biomass as non-conventional, and I've also defined ash as non-conventional. Now, next, what are the typical outputs that I would be getting out for gasification of biomass? So the first thing would be hydrogen. So I write H2, and it should be taking the element automatically. So the H2 gas is there, it's conventional, it's coming the component name and the alias. There's another way I can do is I can go to the find option. Say the other option that I want is like I write CO and I go to find now. So it has a big database and it's going to come up with different amount of chemicals. So I can select carbon monoxide from here. And as you can see, like it has pretty extensive database. And that gets added in here. So that is carbon monoxide. I can change the name for my own convenience. I've written CO and I can press carbon monoxide. So there are two ways to find a compound. Either I can go to find, and either I can just, if it's a typical compound like hydrogen, carbon monoxide, or CO2, I just type in CO2 and the compound is readily available. The other thing that would be apart would be methane. So yeah, any syngas would have these four major components. It would have hydrogen, carbon monoxide, carbon dioxide, and methane. So that is the major component of any syngas that you get from the gasification process. Now, I would also require air for the gasification process. So I need to give in nitrogen. I also need to give in oxygen. So these are the components that would be required for nitrogen and oxygen. Now, there might be some amount of carbon formed. So I give in carbon, which is C, and this is giving me carbon graphite. There could be some sulfur that is being formed. So I have sulfur in here as well. There could be some chlorine. So these are the compounds that I can think of right now. So it has biomass, it has ash, it has the different gases, and the different compounds in terms of carbon and sulfur that might be required for this example. So this is how I'm going to define these components. And I might need sulfur as a dye compound. So that we will enter if that's needed later on. Now, the next step, so the easy thing of this is I can just press this next button and the software is going to take me automatically what is the next input that would be required from me. So I press this next button. So the next thing that it wants me is to satisfy or to give the properties. So here is a list of all the property packages that are available. So it's pretty extensive. And as I told you, like these kinds of system would work very fine with the RKS system. So this is a property system that I have assumed. Next would be the correlations between the different systems. So these are the different coefficients that are already available in the software. And these are the data banks that are available. So this is where the importance of system again comes into play. It has a lot of information available of all these compounds. So I just press next and it's going to calculate all the things. So now comes the non-conventional parts. Now, if you remember, we had the biomass and the ash defined as non-conventional. So we need to give the properties. How is Aspen Plus going to determine the enthalpy and the density of those? So we already have options for that. So the basic properties for biomass would be H-col gen and D-col ist. So these are the basic property packages. The definition, if you want about this, you can go and read about them. It's easily available. And you can change these options as you can see 1, 1, 1, 1. And these are basically giving you how the enthalpy of this biomass will be calculated and how the density of this biomass will be calculated. And the inputs that it would require would be proximate analysis, ultimate analysis, and sulfur analysis. So these are the things we already have as input: the proximate analysis, the ultimate analysis, and the sulfur analysis. Again, to reiterate, in case some of you not remember about the proximate analysis, so if we start with biomass and we start heating it, the first thing to escape the biomass would be moisture. All the moisture that is present in the biomass would evaporate and escape. So that is the moisture content. The second thing to escape would be the volatile matter. If I'm not providing in any air or oxidizing agent, all the matter inside biomass will slowly oxidize and move out of biomass, leaving the black carbon behind. A typical example would be, if you remember any bonfires that you have attended, after burning the wood, after burning is the black part that is left. So that black part is nothing but carbon after all the volatile matters or the different polymers in terms of hydrocarbons escape from the biomass. So that is basically the volatile matter. A normal biomass would have somewhere around 80% of this volatile matter. The carbon that is left behind is fixed carbon that won't go away if you keep on heating the biomass in the absence of air. If you combust it, this fixed matter would also go away, and what is left behind is the ash, the gray thing that is left behind, any bonfire. Like that's nothing but the elements like silica or potassium or calcium, which form the ash, which should be of the range of 1 to 2% in any conventional wood. So this is what I mean by the proximate analysis. By the ultimate analysis, I mean the different elemental compounds, and by sulfur analysis, the types of sulfur that are present in the compound. It makes much more sense when we are dealing with coal. So you can also model a coal gasification process using a similar methodology. But since our aim is biomass modeling, we are focusing on biomass. So I've given this for biomass, and a similar thing can be given for ash as well. I've selected the same property parameters for both coal and ash, and this is how I have defined the two components, which is biomass and ash. And I would press the next key, and it would do a property analysis. And it says that results are available with warning, which means there are certain components which might cause some problem, but not a big issue. And we can go ahead with them. So we have the properties that would be required for a system of this sort. So we can easily go further. Now the next step would be to go into the simulation domain. We press on the simulation thing. And we come across a window like this.
So
this is, yeah.
Sir, what are the properties of ash?
So the properties of ash is nothing but like how to calculate the density and the enthalpy of ash. And this is basically done by using the correlation that I've given you. Something very similar to coal.
Yes, sir. Means which option we have to choose?
It's the same option that
Okay,
I chose for biomass. Okay, so now we are into the simulation window where we can make the whole flow sheet. So let's start with a basic reactor. Let me choose a stoichiometric reactor and put in here. I put the name maybe CUMB, and the reactor appears here. And if I need to put in biomass, I can select a material here, start the equation, and this is where it's going to connect, and put in biomass. And I also need an output from this. So let's put it element. So I'll explain why I put an element in here. So let's do with this first. So I'm putting in biomass in here, which means I'm inputting biomass. So I need to give in the composition. Again, before we start, we also need to make one change. Since we are dealing with non-conventional solids, we have to go to the setup and change the stream class to take in non-conventional components as well. So now when we go into the stream, it will show us two, the mixed and the non-conventional. Mixed means any typical compound like hydrogen, carbon monoxide, carbon dioxide, methane, N2, O2, carbon, or sulfur. So remember, these are the compounds that we design that we described in the initial part of the simulation. So it will take only those compounds which we have defined. It won't take any other compound that we haven't designed. But our input doesn't have any of these. It just has biomass, and the biomass I can get in here. So I would assume biomass going at 25 degrees Celsius. So here I have to give in the temperature and the pressure. I would assume 1 bar. And the mass flow I have around 1 ton per day, 1000 kgs per hour. And here again I can write in either the percentage or the mass flow. So you can see here, I can give it in different ways. Either I can give the mass fraction, the percentage of mass that is the biomass belonging to, or the flow rate. Even here, I can give the mass or the volume flow rates. The next thing would be to describe what the biomass is like. So here we have three properties: proxenal, alternal, and sulfonal. So by proxenal, I mean proximate analysis. So this is where our values would come into play. So I need to give in this proximate analysis of biomass. For time being, let's assume all the moisture has been evaporated. So I will put in 0. And this would be 16.2. This would be 83.8. And ash would be around 1.16. So the moment I give all the values, it turns to be a tick mark in blue. In case any of these values is missing, so if I don't give all these values, comes red. So this is a way to determine in Aspen Plus if the required values have been given or not. The moment it changes into blue means all the values have been provided. So again, I give these values 0. The fixed carbon is 16.2 and 1.16. So this has the ability, the software has the ability to normalize the things. In case I provide the values as 0.162, 0.838, and 0.0116, it would have the ability to normalize it and get the total of 1 and 100. So it doesn't matter like if you are giving it as a total of 1 or total of 100, it will normalize everything. So now comes the proximate or ultimate analysis. Again, you need to keep in it's important that the amount of ash that you put in the proximate and ultimate analysis is same, else you might end up getting errors. So the ash amount remains constant, 1.16. The next thing would be carbon, which would be 47.44. Hydrogen, which is 6.12. Nitrogen, 0.19. There's no chlorine present. Then there's also sulfur, it's 0.19. And then oxygen, it's 45.06. So the ultimate analysis has become blue. But still, the biomass appears to be red, which means still some values are left here. What is it? It's the sulfur analysis. So I go to the sulfur analysis. And since this composition is not available to me, I can put in like 100% to pyruvic and then 0, 0 for both of them. And then you can note that all this have turned blue, which means all the things that are needed as an input have been provided to me. So this is how my input streams are complete. The second thing would be this combustion section. So herein, I again provide certain conditions. Let it be room temperature and pressure. And sorry. So all the like streams as well as the reactors that you open are also available as tabs. So anytime you want to go into them, you can go and access them readily. So that is another advantage. So if I open this, so this is a stoichiometric reactor and I need to give an equation. So the basic equation, the first thing that I will do it, I would have biomass going in. The coefficient should be 1. And the result would be hydrogen, carbon, sulfur, chlorine and oxygen and nitrogen. Now you might be wondering, like, why I'm putting these compounds. So biomass as such, we don't have what are the reactions available for this biomass. So the way to go about it is I first break down this biomass into its element, which is hydrogen, carbon, sulfur, chlorine, oxygen, nitrogen. And I still don't know what the composition is going to look like. And then once I have this composition, I will employ a Gibbs reactor, which will give me the equilibrium concentration of the different gases. So this is how I can model a gasifier in a software like Aspen Plus. So as of now, I have given in 1 mole of biomass, giving me 1 mole of gas. So this is not a balanced equation. I agree with that. And to balance the equation, we are going to take help of a calculator. And we also need to enter in the fractional conversion. This part is still red. So we need to give in like what is the conversion. So I can give 100% conversion. Okay, sorry, it has to be 0 to 1. So 1 conversion of biomass, which means all the biomass gets converted into the different components. So now this everything is blue. This is working fine. And the way I need to run the simulation is just press the next key. Now you can see here, this is saying all input required input complete, which means everything that I need to run the simulation is complete. Say if this equation was not done. So this says flow sheet not complete. So it means I have certain component, which is this output, which is left. So, and the moment I put in this, we have the required input complete. And the same thing happens, say if I don't put given the temperature here, and which given no temperature, it says required input incomplete, which means I need to put in some things with some parameters which have not been provided, which is the temperature in this case. Once I have this, it will give me required input complete. Okay, so sorry for this. So once I have all this, I can run it, and it's not going to give me anything, just showing you this is how the simulation results, and it's going to give me errors. The reason is that because this simulation, like this stoichiometry, is not correct. 1 mole of biomass giving all these compounds. And for this, we need to go into the calculator block. So with this, let me go into a predefined flow sheet that I made already for saving time, but we will have all these options. So what I have done is, we have all these reactions. This is the same reaction that you have. And we also have a calculator that is defined. So what it is being doing is, it has the components taking in, and let me define it for you. So let's the biomass. So what I'm doing in here is, this is the input biomass, and I have to define it as it's the flow rate, the stream from which it is coming in, the substream, which is the non-conventional, the component name, and its flow rate. And once I define these components, I can divide it and get the composition of the different compounds, which are in terms of sulfur, chlorine, nitrogen, hydrogen, and carbon, which is coming from the ultimate analysis. So in essence, what I'm doing is I've written a small code wherein I'm getting all the percentage of different elements in the biomass as I defined earlier, and now dividing them into individual compounds. So this is what I am been doing. So this is the only way to do a simulation which is based on biomass. I know that is complex, but bioenergy systems are complex. So you would need to write certain equations like this, and maybe I'll give you an example of that. Say I'll go to the flow sheeting options, go to calculator, new, let it this be C1, and how to define this. So say I want to define the biomass input. So I give it a variable name, which is biomass. And then I need to select the variable that is here. So if I need to select the mass flow, I can just give the biomass and it will give me the options. And this is how easily I can select. So it is automatically going to give me the options. What are the options available to me? I'll go through it again. So I define a new component and I need to take from the flow sheet the flow rate of biomass. I define a new component which is called biomass, and these are the different variables that could be derived from a flow, flow. And what I would need is a flow variable or mass flow. Then it asks from me the stream. So there are just two streams available in this flow sheet, which is the biomass and the element. So the stream I would choose is biomass. Then the substream would be non-conventional since it's biomass, and the component would be biomass. And this particular table is going to fetch me the value of biomass. So we have to write a calculator block like this. And for the ease or for saving time, I will copy the calculator block that has already been available with me from this example. So you can copy these. So this is there, and I can just copy this. But the only thing I need to keep in mind, the names have to be same. It should be biomass and atomic. So I would need to change this name. And I can go to the first calculator option. And we have a paste option here. Again, you can see it has not taken certain values. The reason being the change in the name. In this case, it's biomass in, which is giving in. So let me change the name again to biomass in. So what I'll do is I'll delete this calculator. I will rename the stream. Okay, let me check it again. It was biomass in. Okay, and I can go and paste it again. And this is going to work in fine. But still I have something to define. So let me see what is on it. Okay, we don't have the component water. So we forget about defining water. Water is an important component. So how do we do that? So we go to the setup, components, and define water. Okay, so again, here water isn't coming. The reason is I press H20. So we need to give the actual name is H2O. And if I do that, it has automatically on water and H2O. And if I'm adding a new compound in here, I need to run this simulation again. So all the parameters will be estimated again. And this is done. So we need to define the water in here. Now we have H2O and the ID3 would be mixed. And the other compound that is here is sulfur. We have sulfur in here and this is mixed. So you see here. So what I'm actually doing is, first thing is I'm defining water, which is the moisture content coming from the moisture content, and subtracting 1 minus moisture content gives me the dry biomass basis. The proximate analysis or the ultimate analysis is always on the dry basis. And based on the dry basis, I multiply with the percentage of biomass. So alternate 7 basically represents oxygen. So this is what I'm doing, oxygen into dry, and the amount of biomass into the air is 7. And I'm multiplying that with the molecular weight of oxygen. So suffice it to say that I've broken down biomass into its ultimate analysis. Keep it that simple. That would make simulation easier for us. So once this is available, if I run the simulation now, okay, so it's still giving me error. Okay, now the thing is that now the ash, I haven't defined anywhere what the ash is going to look like. That's why it's giving me error. So where do I do that? I do that in this system again. So this is where I need to go for the component attributes. I would select a non-conventional. I would go to ash and I would approximate. So ash is nothing but 100% ash. So I'll give it 100% ash in here, and it's good enough. Even in ultimate analysis, I can give 100% ash, and it wouldn't have any sulfur. So 0, 0, and 0. So if I run my system again, I just have to press the next key and continue. Okay, so it has not been able to run because we have not purged out the results. So every time you run a simulation again, you need to present the reset, which means you are purging the simulation again, and then rerun the equation. Okay, I'm still getting certain errors because it's not in mass balance, which means there is certain error that is being occurring here. So let's try to figure that out. Well, let's figure it out later. So we have this biomass that is coming in, and then now the next reactor that we would require is the Gibbs reactor, and this could be the gasifier. And all I need to do is I need to connect this with the next stream, which is coming in here, and an output gas, which would be syngas. And I define the reaction system in here, which would be 1 bar. And let me define at 850 degrees Celsius, which is the normal reaction temperature. But wait about, where is the air coming in? We need to give in some air as well. So this air would be entering at this point of the reaction, which is giving in air. And since you can see this arrow is outside, which means it hasn't been connected nicely. So I would do it again. I would reconnect destination. So now we have the air coming in as well. And the air would come at around 25 degrees Celsius, 1 bar, and the mass flow rate could be around 2000. So if you remember correctly, the gasification means in an insufficient supply of air. And normally the stoichiometric requirement for 1 kg of biomass would be 5 kg of air. And for gasification process, we normally choose 20 to 30% of it. So 2000 should be a good number. And we all know the mole fraction of air. I can choose mole fraction in here. And I can go for oxygen and nitrogen. So nitrogen would be 0.79 and oxygen would be 0.21. So this is how air is going in. And I purge out all the results and I simulate it again. Again, I'm getting an error in the combustion log. We'll look at it later. And this would give me results. So let's go with this result. And if I go with the mass fraction, you can see around 15% of it is hydrogen. Around 27% is carbon monoxide, around 14% is carbon dioxide, and there's hardly any methane. Around 51% is nitrogen. So this is the normal syngas that you would get from the gasification reaction. So what I have done initially is I've broken down the biomass into individual components and then placed a Gibbs reactor in here. And this Gibbs reactor is reacting with air, and this is giving me the composition of gases. So remember, I've not given in any equation in here. It has calculated all the output based upon the Gibbs reaction. So only thing that is going in, if I can go, like I can select the stream, I can this results. It's the composition in terms of hydrogen, nitrogen, oxygen, carbon, and sulfur, and some amount of ash. So this is basically the same thing. Remember, I have given this composition. So the ash was 1.16, so it's 116. It has normalized the values. Hydrogen was around 6.1, so this is what hydrogen is. Nitrogen is 0.019. Carbon is 47. So this is how it has done. It has broken down the biomass again into its constituents. And this I'm reacting with an insufficient supply of air, reaction going into Gibbs and 850 degrees Celsius. And it's giving me the output in terms of the different gases which I would get. If I can go to the result section here, and this is the mass flow and I can also select the mole flow. So it can give me either mole flows, mole fractions, mass flows, and mass fractions. If I go for the mole fractions, I would get around 17% of hydrogen, 23% of carbon monoxide, and almost 44% of nitrogen. So this again is very similar to a normal gasification process. And also another feature of this is like you can select a factor and go for stream results, and it will give you the input streams and the output streams as well. So you can see what are the mass flows going in. The mass flows are basically the air just has nitrogen and oxygen. This is the atomic part of the biomass. I've broken that into different elements, which is ash, hydrogen, nitrogen, oxygen, carbon, and it also has ash in it. If I go the mass flows, it has this amount of ash in it. And the Gibbs reactor has given me the different composition of the gases, which involve like hydrogen, carbon monoxide, carbon dioxide, and methane. So I can get a combination of all the elements that I can get from this reaction. But wait a minute, this reaction system would be consuming some heat. So you go to results. This means this is producing some extra heat. And the way to do it is I just go to the reactor and press results. And this would give me the amount of heat that is being generated. Since it's minus, it's generated. So kilowatt means it has some extra heat being generated. And if I go to this component, it also has some heat being generated. So why not combine them? So what I will do is I'll take a heat stream. So there are different types of stream. One is material, one is heat, and one is work. So you can define all the types of stream. I'll take this heat stream, connect it from here, and connect it to this, which means now they're heat integrated. And I would name it as Q. And go back and do the simulation again. I'm still getting an error here. We'll go that into later. But again, if I check the output, okay, so I'm getting a very high temperature here, which means I'm giving in more the air that is required. So I can reduce this, or this might be the reason of this error. So in the interest of time, let me go to the already solved example, which is something very similar, which I have designed. And so this is what is happening. I have 1000 kg per hour of biomass going in, which is similar. And then the air that is going in is 4000, which means I am required, oh, sorry, this is not the air, this is the air. It's around 2000 kgs per hour. And I've compounded this comb reactor with the gasifier reactor. The comb reactor is basically used to split the biomass into different components, and the gasifier is a Gibbs reactor, for which I haven't mentioned the temperature. I'm just giving the gas, and the syngas that I'm getting has the following composition. Okay, I need to run this. Results are available, and okay, so I can press on the syngas, and you can see the temperature that I'm getting is around 830 degrees Celsius, which is a normal gasification temperature. And I haven't calculated this temperature. I haven't not given any temperature to it. It is something that it has calculated on its own. So this particular models have the potential to give you the output temperature of the gases as well as the composition. So it is giving me, and it's almost 100% vapor phase. The mass flows are within the range. This is the exact mass flows, and if I go for the mass fractions, it would be around like 15% hydrogen, 27% carbon monoxide, and around 4% water. The nitrogen should be around 50%. So this is how it is giving me the syngas. Now, what do I do with this syngas? Now, that's another question. So one thing is that I can do with the syngas is I can go it for chemical production, like I have done in the case of ammonia. Or the other thing is I can combust the syngas at my own leisure. So I will take you through this example where I am combusting the syngas and producing electricity. So for combusting the syngas, I would need more air. So I provide in 4000 kgs of air as well. I give in the composition in terms of nitrogen and oxygen. and this reaction into the combustion reaction. Here I've given in, I don't given a temperature, I've given a pressure of 10 bars because these kinds of boilers are normally on high pressure. And reaction, it already has a inbuilt feature for combustion reactions. I just press on this, I don't need to give any reaction on this. So it will combust everything. So if I go with the stream results for this particular block, okay, so let me, so this is the syngas coming in and the output of this is flue gas. Okay, so the gas is coming at around 800 degrees Celsius. It's getting combusted and reaching a temperature of 2000 degrees Celsius. And the pressure has increased from 1 bar to 10 bar now. And if I go with the composition, earlier the gas had hydrogen, carbon monoxide, methane. Everything has now been turned to zero. Everything has been combusted. The water content has increased because the hydrogen would combine with oxygen to produce water. The carbon dioxide content has increased because all the CO and CH4 will react with oxygen to produce more CO2. The content of ash would almost remain the same. And then we would also have the sulfur and the N2. There would be an increase in N2 because I'm giving in more air. So this is how I can combust this syngas. And this gas can then be an input to a turbine. So this is a gas turbine, which I want to model. And there are standard models available. So I would choose a standard isentropic turbine, and the discharge pressure I choose to be 1 bar. So I've compressed the gases in the boiler to around 10 bars, and the discharge of the turbine would be 1 bar. So a turbine basically uses the pressure differences between the output input to produce energy. I can give in the isentropic efficiency as well as the mechanical efficiency. I give it 0.7 and 0.9, which are normal. I have different options. I can select the turbine based on different methodology, which could be ASME, GPSA, or is either like piecewise integration. So if anyone wants to explore that, that is also available. And what this is going to give me is the energy being produced. So if I press results here, if I'm providing in this gas and like running the turbine at 10 bars and the output is at 1 bar, it can produce 1.5 megawatt of energy. Since the mechanical efficiency that I've taken is to be 90%, like the indicated horsepower is around 1.6 megawatt, whereas the actual horsepower that I'll get is around 1.5 megawatt. This is basically coming from the 90% mechanical efficiency that I've given. But still this gas is not has a lot of like energy in terms of the temperature. If I go and calculate the temperature of this, so this is turbo out. Yeah. So this gas is still at a raised temperature, which is around 1500 degrees Celsius, which means I can raise in more steam. So why not devise a cycle of turbine which can extract more heat? So what I can do is I can use this temperature in this stream to raise steam, and that could be used with the help of a steam cycle. So the first thing I need is I have defined in a heat exchanger which would provide in heat, or like which would exchange heat with another heat exchanger, and I have asked it to reduce the temperature to around 120 degrees Celsius. This is where I'm stating it. So I'm reducing the temperature from 1500 to 120 degrees Celsius, and this is then being used to raise steam. So we have water coming in. So we have water at around 65 bars and around 30 degrees Celsius that is coming in. And I'm using this heat that is available from this stream to increase its temperature to around 490 degrees Celsius, which gives me a high pressure steam. So this stream can then be used to run another back pressure turbine, which has a similar configuration, 70% isentropic efficiency and 90% mechanical efficiency. And this can give me more energy. And if I go with the brake horsepower, it can give me another 5 megawatt of energy. So 1000 kgs per hour of wood has the potential to give me around 2 megawatt of energy. This is what I'm trying to prove, or like I'm trying to simulate. So if you have 1000 kgs per hour of wood available, this is how you can define or a gasifier and the type of energy that you can convert. And you can play around with the efficiencies, which is whatever is applicable. And this is a normal cycle. You have the high pressure steam going in, and this is the exhaust, which would have a low pressure steam, which is around at 1 bar and 133 degrees Celsius. I can cool down the steam in the terms of two condensers. The one is bringing it to around liquid at 100 degrees Celsius, and this is further cooling it to room temperature. And then I am pumping it again to 65 bars. So this water is at 1 bar. So this is a normal steam. And these are the kind of loops where I would require the tier steam. So this is where like the tier steam comes into play. So this is an example of this, and I have a heat exchanger. So this is one way of defining a heat exchanger. The other way could be, I'm showing you again. Now this heat or this steam, as you can see, is still at 120 degrees Celsius. So it still has some temperature, and this could be used for drying of biomass. And that's why I defined here an inlet outlet heat exchanger. I can define a heatlet like this is the biomass coming in and biomass going out. So if I go to the stream results for this particular section, so this is the biomass in and the biomass out. So I can raise the temperature of biomass from 25 degrees Celsius to around 70 degrees Celsius by cooling the steam by 10 degrees Celsius. So you need to keep into account in this that the temperature of the hot steam, the inlet and the outlet must be higher than this, because heat can only flow from a higher temperature to a lower temperature. And this is how you would define it. So I can go back to the main flow sheet, and this helps me in heating this biomass. A heated biomass means I can do it even more efficiently. And we have the flue gas that we can exhaust to the atmosphere, which would be mainly nitrogen, water, and carbon dioxide. So you see the nitrogen is here, some excess oxygen is here, and hydrogen is there. We also have some ash, which we need to remove in here, which I have not done, but can be easily done. So this is a simple simulation example that I wanted to show. So sorry, I have not done it step by step in the interest of time, but just to give you an example, like how a simulation can be formed. We have the biomass coming in, we break down the biomass into its element. These elements then gets converted into the gases, and it can also take care of the composition, which is in match with a conventional gasifier. You can combust this gas, and then this gas can be used to run a turbine to produce electricity. And this let down steam still has more energy, which could be used to raise steam. You can raise steam at around 65 bars and 500 degrees Celsius. Then another turbine produce still more electricity. And then this kind of steam can be used as an inlet outlet exchanger. So an important feature of this kind of software is that it enables you to do a lot of heat integration, how you can utilize the heat that is available in one place to another place. So this is the application as well. With this, I would also like to give you a glimpse of like how complex the simulations can get. So let me first take you to the simulation of the ammonia case, which you have been seeing in the earlier example. So yeah, so this is the presentation that I gave in the first half, and where I was trying to produce ammonia from biomass. So this is how complex a gasifier can get. So this is the same simulation for the dual bed gasifier. So this is the kind of system that I could derive from the CFD simulation, which is a components of various CSTRs and PFRs. So these have further equations being written into it. If I go into the reactions, you can see here I mentioned R2. And what do you mean by R2? I can go into the reaction section, I can go into the R2, and you can see these are the kinds of reactions that are occurring in here. So I've defined all this reaction, and you can do that as well. And you can give the kinetic parameters, which means how fast the reaction is occurring in terms of this equation. So in case the equations are available to you, you can use these kinds of parameters as well. So yeah, in this case also, the biomass is coming in, it gets spiralized, and then there is a specific function of the different like breaking down, and finally the reactions are occurring in all these reaction systems. And these are the CSTRs, the PFRs. Like if you remember from the earlier example, it was a loop here, and then this is the middle part of the reaction, and this is the final part of the reaction. And the syngas that I'm getting, so let me show you, like this should be the syngas. And if I go with the mass fraction, It has almost 18% carbon monoxide, 29% carbon dioxide, and 23% hydrogen. So this is syngas. And then this enters into the different reaction configurations, and which has a lot of loops. You can see like there's one recycle here, another recycle here, and so a typical system would have a lot of recycles. You have this as being a desulfurization unit. Then this is a shift reactor for conversion of carbon monoxide to carbon dioxide. So you can give the configuration, what is the size of the reaction be like. You can give in the reaction system. Here I've chosen R3. And if I go again to reactions, you can see what is R3. This is CO plus H2O, giving CO2 and H2. And you can define the kinetics in here. And this is an ammonia loop. And the final thing would be the product, which is ammonia. And if I go with the mass fraction, you're getting 99% pure ammonia. So this is the kind of simulation that you can derive using the software. I've shown you like how this software can be used for production of electricity. The second simulation, which is a bit complex, but to give you an understanding, this could be used for production of ammonia. Still a complex equation, maybe for the next couple of minutes, could be something like this. So this is with respect to the algae production. So this appears to be a simple one, but when we are dealing with oils, we would have like a very different, like the bio-oil is a combination of very different compounds. So let's take this PBR, which has grown in wet algae. So if I go with the mass flows, the only thing that it has is water, which would be 80%. And the other thing would be algae. And if I go with the mass fraction, it should be around 80% of water and 20% of algae. And after making it go through a set of reaction, which is HTL, which is again a complex system. So let me show you this. This should be interesting. So if I have this reaction that is occurring at around 350 degrees Celsius and around 200 bars, and you can see the input is, okay, so let me do it in the mass fraction. It is around 80% water, and the remaining would be algae. And these are different kinds of compound that I'm getting in terms of bio. It would have methanol, ethanol, acetone, acetic acid, protic acid, and there's a toluene, phenol, indole, like these are C15, C16, and C18 compounds. So Aspen gives you the feature of defining all these components. And I can also use this to get the final composition of the bio-oil. So this is the final flow rate in terms of like the temperature, and the mass flows. I can see what would be the composition of the bio-oil, which could be really complex. So it gives you the facility of doing any kind of system, be it production of bio crude, electricity, or different chemicals. So with that, I would like to take a hold. Let me know if any one of you has any questions regarding this. I would be happy to answer. Okay, so if you don't have any question, maybe I'll go through, like I'll take 5 more minutes and maybe explain this sheet even further to you, if that makes sense. So this was the kind of system that I was explaining in here. Like this is the kind of system that I explained in terms of the biomass going in. So this is the biomass going in, getting decomposed. It's very similar to the system that I just designed. The biomass is getting broken into the systems. I'm burning biomass, and then I'm producing electricity out of it. And then you get the syngas or the flue gas, which is nothing but CO2 and nitrogen. So if I see here, like it has almost 23% of carbon dioxide and the remaining is nitrogen, around 64%. So you can use this gas for production of LG, and this gas is coming outlet from here, getting combining in here and going to the PBRs. So PBRs is, this is the reaction where I'm producing LG, and this is the kind of reaction that I have. So let me go to the edit phase. So we have the carbon dioxide, water, ammonia, and phosphoric acid going in and producing Lg and oxygen. Now remember, like this is the opposite equation. In the earlier equation, I was breaking down biomass into individual components, but in here I'm combining carbon dioxide, water, ammonia, and like ammonia and phosphoric acid is basically the nutrients that I would need to produce Lg and oxygen. Something similar to the photosynthesis reaction. So I can go either way. I can either disassociate biomass or I can form biomass. So this gives me the ability to do both the things. And then this is the PBR. And from the output, we get subject it to a hydrothermal liquefaction. So this is how a normal simulation would look like. It would have a lot of pumps, which would give you the energy consumption, a lot of heat exchangers, where the energy is getting, and a lot of cyclones for removal of things, a lot of flash drums, a lot of valves. So you can design a real life plant in this. So yes, so this is what an actual simulation looks like. And most of the basis of the reports on the literature that you study regarding biofuels are based on simulations like this. Maybe with this, we can take a stop. So if anyone is interested, please feel free to ask the questions. I know it could be a bit of much more technical. If yeah.
Sir, is there any manual for handle these softwares? Actually,
there are manuals available.
So with this is a proprietary or it's a free?
Yeah, it's a proprietary software. It's not a free software.
Okay, sir. Okay. And how much the cost of these softwares?
So the educational license is almost $2,000 a year. Like it's an yearly license.
Okay, sir.
So it costs something of this range.
Okay, sir. Thank you, sir. Thank you.
Hello.
Yeah.
Good afternoon, sir. Sir, in biomass thermal power, I have one question related to biomass thermal power plant. In bio.
Sorry, I'm not able to hear you. I believe someone was asking the question and I wasn't able to hear it. If needed, you can type that in the chat box. So yeah.
Hello.
Yeah.
I'm audible, sir?
Yeah. Please go ahead.
Okay, sir. My question is, in biomass thermal power plant, what is the percentage of fly ash content?
Okay, so the ash content would normally be a 1%, like that is. There's very less fly ash, like as compared to the coal plant, and most of that is settles down. So there is hardly any fly ash, and most of the ash just sinters down. Like there's a concept of sintering, so it just melts, and you can get it in the bottom of the gasifier. Okay. So you don't need to worry about the fly ash.
Okay, sir, this software is used for maybe like that. We can use this software for biomass co-firing thermal power plant.
Sure, yeah.
A simulation for that.
Yes, of course you can.
Okay, sir.
So you can define the coal in a similar fashion as you did with the biomass. The only thing would be a coal would have a different proximate and ultimate analysis. So in the case of coal, where you're giving in biomass in here, this fixed carbon would be around almost 80%, and this would be 20, maybe 15%. So this is where like the change would be.
Okay, sir. Okay. Thank you very much, sir.
Okay. So in case if there are no further questions, thanks for being a great audience. And in case you have any questions regarding this, feel free to mail me. I would be more than happy to answer any of them. And with this, we close today's session, which was the hands-on session on biomass modeling. So the first session was the basics of biomass, and the second, we went through the different types of simulations that can be encapsulated. It could be at the phase level, process unit level, or the plant level, as well as the global level. And today we got like somewhat experience on the type of softwares that could be used. Since biomass is not a very widely used energy, there are limited softwares, and this was one of the software that has been used extensively for modeling bioenergy and biorefineries. And with this, we end today's session. Hope to meet you all for tomorrow's session, which would be focused on hydropower. So looking forward to meet you all tomorrow morning at 9:30. Thank you.
Thank you, sir.
Thank you, sir.